So I'm going to talk a little bit today about a project in motion, shall we say. This is an in-progress cost-benefit analysis for EM. That's a collaborative project between myself, Seb, and Verity in the Biomaths and Risk Research Group at Weybridge, and then Richard Budgie in APHA's Wildlife Management Centre. So really briefly, since this is a project in progress, I'm going to take you through some of the aims and the background and how we're doing, how we're defining the costs and benefits, and then bring you up to date with where the data is so far. So in terms of aims and kind of purpose of this, I don't have to tell any of you, I'm sure that it's a good idea to look at your surveillance systems while they are live, so to speak, to make sure that they're still providing good kind of value for money and delivering on their objectives. So this has given us two kind of main aims for the project. Firstly, to provide a cost benefit ratio looking at the current surveillance and then comparing that to some of the alternative options out there. And then using that to showcase to our stakeholders which of the approaches kind of gives the best benefit, the best bang for your buck, so to speak. So we had two main tasks to fulfill this. Firstly, as you can imagine, a cost-benefit analysis of these surveillance options. So that's looking at things like varying the diagnostic test or the sample numbers, etc. And then to feed into that, modelling the number of years until detection in the red fox population. So a little bit of background about what EM is and why we care about it. So broadly, it's a tapeworm that affects canids. From our point of view, that particularly means that we're looking at red foxes and domestic dogs. But as you can see from this lovely diagram that I have borrowed from the CDC, it's a multi-stage life cycle. So it also includes microtine rodents, so that's things like field voles, etc., as intermediate hosts. And on the right-hand side, we have a human. Unfortunately, it is a zoonotic disease. We're not meant to be involved in this. We are aberrant hosts. But if we do ingest the eggs accidentally, we can develop a clinical disease called alveolar echinnoccoccosis, which for my own sake, I'm going to refer to as AE for the rest of this. It's not a particularly great disease. None of them really are, but this is lifelong with a very long incubation period of up to 15 years. And it involves the development of cysts in the liver, which can lead to things like jaundice and impaired liver function, as well as abdominal pain, etc. And it can also move to other organs, lungs, kidneys, brain, just to give a few examples, which can lead to some other pretty nasty symptoms, such as headaches and migraines, vomiting blood, things like that. So we really don't want it, particularly given that it's lifelong. In terms of treatment, then we have some options for stopping it in its tracks. So there's chemotherapies with drugs such as albendazole or mebendazole, and in some cases, surgery. But equally, it's not curative. It's just to keep it at bay. And to give you an idea of the kind of burden of disease, if we just briefly talk about dailies, it's given the same weight as pre-terminal liver cancer. So something we really want to avoid. Now, I mentioned definitive hosts as foxes and domestic dogs. In rare cases, domestic dogs can actually develop AE as well with similar symptoms to us. And they have similar treatment options with the kind of last line outcome of euthanasia. So we also really want to avoid it in our pets. Now, unfortunately, it's also widespread across the Northern Hemisphere. So there's focal areas in America, Canada, France, Germany, quite a large burden of AE disease in China, etc. So that all sounds reasonably grim, but I do have some good news. There's no recorded domestically acquired cases in Great Britain, and we'd really like to keep it that way. So with a few exceptions, dogs have to be wormed ahead of bringing them back to GB, and that's whether they come in via the pets travel route or whether they come in as a commercial import. And on the back of that, we also conduct annual surveillance to demonstrate freedom from disease at 1% prevalence in the red fox population with 95% confidence. And that is the surveillance that we're evaluating in this. So a very brief note on Matrix, because I appreciate I'm running a bit short on time here. Matrix is it's a project that has produced a set of guidelines for designing, implementing, and evaluating output-based surveillance systems, of which echinnoccocus is a good example. So we're using these guidelines, or the economic analysis portion of them, to drive how we do the work. So on to how we're defining the costs and the benefits. On the left-hand side, we have the costs. So we have things like the cost of the surveillance system, the cost of the diagnostic testing, things like that, and then the cost of worming dogs when they return to GB. And in the corner of the benefits, we have the human and the dog cases averted. Now, those are very top level headings, I think, really. There's some sub-factors within that, as you can imagine. So I've mentioned surveillance and varying diagnostic tests and sample numbers, and the worming of dogs for commercial and pet movements. For the human cases, we're looking at the cost of a community case versus the cost of hospitalisation, and whether that changes with how early it is diagnosed, because it's a fairly underreported disease, and similarly the cost of various treatment options in dogs. So I'm going to metaphorically zoom in on the cost of surveillance for a second to give you a look at some of the data types that we're collecting for the diagnostic tests. So I should say that the data in this table is placeholder data. It's not a true representation of what we are seeing, because we're still collating that because it is still in progress. But as I mentioned at the very start, one of the aims of the project is to compare the current surveillance to some of the other options out there. And this is how we're going to go about this. So the egg flotation and PCR is the current surveillance, and we're going to be evaluating that against a couple of other options. There's actually more than I've put into this presentation, because I seem to keep adding them, but never mind. So what we're looking at really is collecting data through literature and expert opinion on things like the throughput, which will feed into the staff time at the bottom there, the test sensitivity that people have reported, which can feed into the number of samples that we need to take per year, and then based on the published methodologies, an estimate of the consumables and reagents cost. And all of that, along with the operational costs and additional costs, will feed into an annual cost for each of these now 6 different testing options. So we can have a kind of top level at a glance which one looks better than the other. But as I mentioned earlier, it has quite a long incubation period, and it's also a lifelong disease. So I think it's only right, really, that we scale this with the number of years until detection. So to do this, this is not my forte, so I will do my best to explain this. We are using a model written in R by Richard Budgie of APHA Wildlife, and it uses the red fox population along with the parameters that I've just spoken to you about to model the number of years for each test type between the initial incursion and the first detection in red foxes. And this is really important, because we may have a test, if I just flick back to here, we may have a test that is, for example, really expensive for consumables and reagents and staff time, but it might detect it in 18 months because it's particularly good at detecting pre-patent infections. And if we compare that against a test that is really cheap, let's say it's less than £3 and it costs an hour's worth of staff time, but detects it in 10 years, that would skew the benefit of the test effectively. We then rinse and repeat all of that for the parameters that I showed you in the table, so the worming and the human and dog costs, and feed that into this lovely equation along the bottom, which is the cost benefit ratio. Really broadly, it's benefits divided by the costs, and it'll give you a number above or below 1 to say that what you're evaluating is more beneficial or more costly, depending on the output. But wait, there is more. So the last thing we're going to do in terms of taking this to our stakeholders is to put this into a report where we can then talk about things that are non-quantifiable costs. And that's whether it's because there's no data or maybe it's out of scope for the project, but it's still really important to include. So we are currently gathering data on things like the impact of losing our freedom from disease status, the benefit to other surveillance systems. For example, the worming will cover other pathogens. There's a shared benefit there. Things like the emotional impact of human and animal illness. Particularly, I mentioned that from an animal perspective, one of the outcomes is euthanasia. And then finally, incorporating a discussion around kind of cost and efficacy of eradication measures and methods were it to become established, because the literature very much looks like it's been an up and down journey for other countries, shall we say. And that brings me to my end of my crash course, I guess, in cost benefit of echinnoccocus.